So let's go over the idea of elastic and inelastic collisions, because a lot of the bulk of the questions that you have in your assessment are related to this concept of what it means for a collision to be elastic or inelastic. And the idea is very, very simple unless you think too much about it and complicate it for yourself. So the idea is that for elastic collisions, kinetic energy is conserved, whereas for inelastic collisions, kinetic energy is not conserved. So basically, if we have two objects, like these, mass m1, this is moving at some speed u1, this is some mass m2 which is moving at u2, and you know that collisions can occur even if this u1 is greater than u2, so this catches up, m1 catches up to m2 and hits it from behind, or if u2 was also directed towards the left, right? So it could either be moving in this or in this direction. It really doesn't make any difference to whatever this is that I'm going to discuss now. And after the collision, so if after the collision these are moving with some velocities v1, again it could be in either direction, and m2 is moving in either of those, could be in either direction. The idea is that the kinetic energy before must equal the kinetic energy after the collision, right? So this the kinetic energy of all of these particles on the left must be equal to the kinetic energy of all the bodies on the right. So half m1 u1 squared plus half m2 u2 squared should equal half m1 v1 squared plus half m2 v2 square. So don't focus on this too much. This is just an expression that came about due to this. It's a consequence of this. What you must worry about more is how do you actually use this in certain scenarios. So actually I must add here that the total kinetic energy before should equal the total kinetic energy after the collision. Also, you might have seen that I don't really care about whether any velocity, final or initial for that matter, is either to the right or the left, because energy is a scalar, right? And this formula for kinetic energy, half mv square, depends on the speed, not the velocity, right? So we really don't care about whether where it's moving, to the right or to the left. So if I make a table of values just to see for myself what quantities change, what quantities do not change, and which ones do not in inelastic collisions. Trying to get a hold of this guy, yeah. So actually I think we need another one here. So if we have any type of collision, we'll be talking about whether kinetic energy, momentum, or the total energy for that matter, which of these quantities are conserved and which ones are not. So for elastic and inelastic collisions, The idea is that, and we just talked about this, that for elastic collisions, kinetic energy is conserved, but for inelastic collisions, kinetic energy is not. But regardless of whether the type of collision is elastic or inelastic, the principle of conservation of momentum still holds true, that the total momentum is constant. And similarly, the principle of conservation of energy also holds true, that the total energy in elastic collisions and as well as inelastic collisions is constant. So something else about the different types of collisions. So whenever we have any collision, we could be asked if it whether it is elastic or inelastic, depending on whatever mass and speed values are given. But one thing you must always remember, and this will speed up solutions to MCQs for a lot of the cases where such thing is actually asked. So the idea is that any collisions where the objects stick together become one combined object, or the examiner may also use a word like coalesce, are all called sticky collisions, and they are always inelastic. Any example of a sticky collision you may have will always have some loss of kinetic energy. And there is some math behind this, but it is quite intensive, and we'll not be going over that right now because it's not part of the syllabus. And if the word algebra does not make you puke, you can also go ahead and do this for yourself. For whom the word does make them puke, let's say it once again. Algebra. So another way that we can talk about elastic and inelastic collisions is through this idea. And again, this is a mathematical expression that follows directly from what we saw above, from the conservation of kinetic energy. And the idea is this, that for elastic collisions, the relative speed of approach equals the relative speed of separation. And if you're looking at this content through a book as well, so you'll see an expression there, but that expression is again highly dependent on how the objects are moving towards one another, right? So how do you calculate the relative speeds of approach? By the way, keep in mind that even though we usually use velocities over speeds when dealing with momentum, in this case we are dealing with the relative speed, right? Not the relative velocity, the relative speed. So in this case we will not really care about these signs, but we will care about how the objects are moving relative to one another. So the idea is this, that if objects are moving towards one another, or actually even better than that would be if we talk about this way, that if the objects are moving in the same direction, or actually if they're approaching each other, they would be in opposite directions. So if the objects are moving in opposite directions, add to get the relative speed, right? Could be of approach, could be of separation. And similarly, if the objects are moving in the same direction, subtract to get the relative speed, right? Again, applies to both applies to both approach and separation. So let's see it using an example. So if the two objects are like these, let's say this has some speed 5 meters per second, this has another speed, let's say 3 meters per second, and we can see both of these are heading towards one another, right? But the speeds are in opposite direction, so we will add them. So the relative speed of approach in this case would be 5 plus 3, which is 8 meters per second, right? Let's make just one change to this at a time. So if this one is still traveling at 5 towards the right, this is traveling at 3 towards the right. So again, we know that this being the speedier one would catch up to this, right? So there is the one in orange is approaching the one in green, but because they have now the same directions, we are going to subtract to get the relative speed of approach. This would be 5 minus 3, which is 2 meters per second. Let's talk about another one. So now, for example, if we have it like this one is now moving at 5 meters per second towards the left. This one is still moving at 3 towards the right. So now we can see that both of these will move away from one another, right? Both of these are being separated. They're going on their own ways. So this time, because again this is objects in opposite directions, and we can see that these are going their own ways, they're basically separating. So this time out we would again add, because they're in opposite directions, to get the relative speed of separation. And in the last one, if this is 5 meters per second towards the left, and if this is also 3 towards the left, we know that this will never be able to catch up to this one, because having the greater speed, this will just continue moving away from this faster than this one is approaching this, right? So these will never collide again if collision happened before. So this is also separation. In this case, again, both of these are in the same direction, so you would subtract these to find the relative speed of separation.